In this presentation, we will talk about electrical power. So, devices that are put in an electrical circuit use energy. Specifically, you could think about a light bulb that lights up, produces light energy, and so that energy is coming from the electricity that's in the circuit. So, if you recall from discussing energy and work, we know that the rate at which energy is converted from one form to another is called power. So power is basically energy over time. It's the rate at which we could produce energy, so how much energy is produced in a certain amount of time or how much energy is used in a certain amount of time. For electrical circuits, we can determine the power that is being produced by a battery by finding the current that's coming out of the battery and the voltage of the battery, and the power is then the current multiplied by the voltage. We could also find the power that's being used by a light bulb, for example, if we knew the current that was going through the light bulb and the voltage across the light bulb. So in general, for any component in the circuit, the energy that's being produced or used is the rate at which the energy is being produced or used is the power, and it's just the current through that component times the voltage. The units for power are watts, and watts, of course, is joules per second. And because we have power is also defined as current times voltage, a watt is also equivalent to current units of amps times voltage. So we could ask a very simple question: how much current is drawn by a 100-watt light bulb when it's connected to a 120-volt outlet? So, there's different wattages of light bulbs. Obviously, there's 60 watt, 40 watts are very common wattage units. So if I have a 100-watt light bulb, I want to know how much current is drawn. So I know that power is current times voltage. So the current that is being drawn by that light bulb is the power of the light bulb over the voltage. So 100 watts over 120 volts would be 0.8 amps. Now remember, the outlet of 120 volts is actually an alternating current, alternating voltage, and that the value for that voltage of the outlet is equivalent to a 120 volt battery. So let's look at another example. Suppose that I have a 120 volt line to a socket that's limited to 15 amps by a safety fuse. We talked a little bit about safety fuses before. Basically, you can't draw more than 15 amps in that particular line of the circuit, or the safety fuse will blow. The question is, will I be able to operate a 1,200 watt hair dryer? So there's two different methods that we could approach this question. We could find the power that's available from the source and see if it's larger than the power that's needed for the hairdryer. That's method one. So in method one, we want to find the power that's available from the actual 120 volt line when it's connected to that safety fuse of 50 amps. So that's the maximum current. So I would take the current of 15 amps, I would multiply by 120 volts, and I get 1,800 watts. So that line, that socket, can actually take up to 1,800 watts, so that 1,200 watt hairdryer would be fine to connect to it. Another method for answering this particular question is to find the current that's drawn from the hairdryer when it's connected to the voltage supply and see if it exceeds the safety fuse maximum. So in this particular case, we would start again with power is current times voltage. I could solve for the current that is being drawn by that hairdryer by taking the power and dividing by the voltage. So the power is 1,200 watts. The voltage is 120 volts, and I get 10 amps. Since 10 amps is smaller than the 15 amp maximum, then the hairdryer would operate safely without blowing the fuse. So it turns out that if you don't already get an electric bill, at some point in your life you will get an electric bill. And so when the power company charges us for the energy that we use, they're not charging us for power, they're charging us for the energy that we've used. And different components or different devices in our house actually use a certain amount of power, or they have a certain power rating, meaning that depending on how long we have them connected, they will use a certain amount of energy. So we know that power is the rate at which energy is produced or consumed. And so if I multiply both sides of this equation by time, I get that the energy that's used is the power multiplied by the time. So for example, suppose I had a 100-watt light bulb in my house, and I had that light bulb turned on for 5 hours, right? I could figure out how much energy that I'm using for that 100-watt light bulb for 5 hours as an example. The longer that I leave the light bulb on, the more energy that I use. So the standard unit for energy in physics is joules. So power would be in watts, time would be in seconds, and then energy would be in joules. It turns out that there's another unit that's often used for energy units when it comes to the power company and for electrical power. And the reason for that is because we get charged for our electric bill once a month. And so that means that many of our components in our house, light bulbs and such, are on for many, many hours a day. And if I had to convert those many hours to seconds, that would be a really big number in terms of energy use, or joules. So in order to get around that, the power company will use units of kilowatt hours. And the way that it works is that the power for any particular component is put into kilowatts instead of watts, and 1 kilowatt is 1,000 watts. So my 100-watt light bulb would only be 0.1 kilowatts, for example. So that's a smaller amount. And our time that we use, instead of using seconds, is hours. So if I multiply power times time, here's power, energy is power times time, and I use units of power in terms of kilowatts and time in terms of hours, I get these energy units of kilowatt hours. You have to remember that 1 hour is equal to 60 minutes, and 60 minutes is equal to 60 seconds. So 1 hour is equivalent to 3,600 seconds. So what does that mean in terms of what a kilowatt hour is in terms of our standard units? So a kilowatt, here's our kilowatt, is 1,000 watts. So instead, I can replace kilowatts with 1,000 watts. And I can replace my hour with time of 3,600 seconds. And I get that a single kilowatt hour is 3,600,000 joules. So the power company uses kilowatt hours instead of joules because typically we use many kilowatt hours. So for example, you might use, in my house, you might use 800 kilowatt hours in a given month, and that would be just a huge number in terms of joules, and it doesn't make sense to charge us for units of joules for our energy use. So we get charged per kilowatt hour. So let's consider an example. We'll go back to that hairdryer. So suppose that I have a 120 volt line to a socket. It's limited to 15 amps by a safety fuse, and it will operate this 1,200 watt hairdryer. Suppose that it costs 8 cents for every kilowatt hour that is used. What will it cost to operate that hairdryer, that 1,200 watt hairdryer, for 30 minutes? Suppose you get really long hair, you gotta really dry your hair, you gotta run it for 30 minutes. So how much is it going to cost to do that? So the total cost to run that hairdryer is going to be the energy that's used in that given amount of time, multiplied by the cost per kilowatt hour. So I need to figure out how much energy is being used to run that 1,200 watt hairdryer for 30 minutes, and then I need to multiply that by 8 cents per kilowatt hour, and I need to make sure my energy is in kilowatt hours. So I know energy is power times time, and I know that the power rating of my hairdryer is 1,200 watts, which is equivalent to 1.2 kilowatts. And I know that my time is 30 minutes, and 30 minutes is equivalent to a half of an hour. So that means that my energy use is 1.2 kilowatts times 0.5 hours, or 0.6 kilowatt hours. And I want to know how much it costs. I have not even used 1 kilowatt hour. If I used 1 kilowatt hour, it would cost 8 cents. So it's going to be less than 8 cents to run that hairdryer for 30 minutes. So the total cost is the energy that's used, so 0.6 kilowatt hours, multiplied by the cost per kilowatt hour, which is 8 cents per kilowatt hour. And 0.6 times 8 is 4.8 cents. So for me to run that hairdryer for 30 minutes, it would cost 4.8 cents. But you know, that adds up, obviously, between running, that's a hairdryer, but running your electric dryer, running your washing machine, running your stove, running your heat pump, running your air conditioner, and so on. All of those costs will add up over time, and the energy use, of course, will also add up over time. So if we go back to the previous examples that we looked at for the series and the parallel connections, we had found that when we had two bulbs connected in series that had different resistance values, we found the current through all of those components that are connected in series was the same value, but the voltage was different. But now we can figure out the power. So the power through bulb 1 is just the current times the voltage, so 0.6 amps times that voltage of 12 volts is 7.2 watts. The power through the second bulb is the current times the voltage, 0.6 amps times 18 volts, so that's 10.8 watts. And the power that's being produced by the battery would be the current times the voltage, so 0.6 amps times 30, which is 18 watts. One of the things that you should notice is that if you add up the power that's being given by the battery, it's equal to the addition of the power that's being used by the bulbs, right? 10.8 plus 7.2 is 18 watts. We can go through the same process for the connection in parallel, and again, this should say parallel. And when we do that, we go through the same process. The power through bulb 1 is the current times the voltage. The current is 0.5 amps. The voltage is 10 volts. So the power of that bulb is 5 watts. The power for the second bulb would be the current, which is 0.25 amps, times the voltage, which is 10 volts, which is 2.5 watts. And then the power that's being given by the battery is the current times the voltage, 0.75 times 10, which is 7.5 watts. And again, even though these are connected in parallel, if I add the two powers from the bulbs that are using energy, it's equal to the power of the battery that's giving the energy.